Hello, welcome to this lecture series on quantum chemistry. In this lecture, I am going to discuss particle on a sphere of fixed radius. Okay, this is actually a model problem. For this problem, we can solve the Schrodinger equation exactly. Okay, right. So let us consider a particle is moving on a sphere. Let me draw a sphere. Okay, yeah. So assume that the particle is moving on a sphere. So this is the origin. Let us take this axis as y-axis, this as x-axis, and this axis as z-axis, and this is the origin. Okay, assume that particle is particle is present here. Let's suppose particle is present here, and in Cartesian coordinate space, we can represent the particle by the Cartesian coordinates x, y, z. Okay. In spherical polar coordinate, you can also represent the particle. I'll join this origin to the particle by a line, and the length of the line is r, and the angle between is plus z axis, and the line joining the origin to the point P is actually called theta, and the projecting angle, if I project P to the xy plane, okay, the projection angle is what we call as phi angle. We have already given that already. So we can also represent this P in spherical polar coordinate r, theta, and phi. Okay. Now let us assume the mass of the particle. Let us consider mass of the particle. It's a particle of microscopic in size. So it's a microscopic particle. So mass of the particle, let it be m. And I am going to make some assumption here. What is the assumption? The assumption is r is constant. R means radius. Radius is a fixed value. Okay, and if potential energy, right, on the ring, right, potential energy on the ring, since r is constant, potential energy on the ring is a constant. Okay, therefore potential energy, since it is a constant, we can assume that potential energy is 0 for our convenience. Okay, potential energy on the ring is a constant. Let us assume that value as 0. Okay, yeah, just for our sake of convenience, so that the solving Schrodinger equation become very easy. Therefore, in this circumstance, the total energy of the molecule is nothing but the rotational kinetic energy. It is the kinetic energy, very specifically rotational kinetic energy of the molecule. Okay, so we are going to show that whether rotational kinetic energy for the molecule is quantized or not. Okay, through quantum mechanics. Classically we already know that rotational kinetic energy can take any value of any possible value. Therefore, rotational kinetic energy is continuous. Classically, that we know. In the last lecture, I gave that point. Okay, quantum mechanically, whether the rotational kinetic energy is continuous or whether it has any quantized value, right? That we are going to discuss here. Okay, so as usual, the time independent Schrodinger equation is for this particle. We can write h psi, where psi now varies with the variables x, y, z, equal to E into psi x, y, and z. So this is the Schrodinger equation we need to solve to find the wave function and the energy. Okay, this is a time independent Schrodinger equation. Okay, you know very well here Hamiltonian operator is nothing but minus h bar square by mass of the particle is m, so minus h bar square by 2m into dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This is the kinetic energy part, plus potential energy should come, since potential energy is 0. Okay, potential energy is 0. We have assumed potential energy is 0, so that part becomes 0 into psi equal to E psi. So this is the expression for the Hamiltonian operator, right? Now what I'm going to do is that this is nothing but the Laplacian operator del square. Okay, you can write simply like this. So you can also write this expression as minus h bar square by 2m into del square psi equal to E psi. You can write simply like this. Okay, now see, this del square is in the in Cartesian coordinate. We have x and y and z operators. Okay, so what I'm going to do, solving this equation is difficult. Why? Because now the wave function depends on 3 coordinates. It's somewhat difficult, but I have a spherical symmetry here. So whenever I told you in the last lecture itself, whenever circular symmetry or spherical symmetry is present, okay, just use spherical polar coordinate in the place of Cartesian coordinate. Okay, so due to spherical symmetry, I'm going to use I'm going to convert this Cartesian coordinate x, y, z into, okay, spherical polar coordinate r, theta and phi. Yeah, now we know very well r is constant here. R is constant. Therefore the wave function psi depends only on 2 variables, theta and phi. Okay, see, when you change the variables from x, y, z Cartesian coordinate into spherical polar coordinate, okay, automatically the number of variables that decides wave function become 2. Why? Because we already fixed the value of r. R is constant. Since r is constant, wave function depends only on these 2 variables. And the standard notation is this. See, whenever wave function depends only on theta and phi, we represent the wave function by the symbol y. Y, theta, phi is the standard notation, and this is called spherical harmonic. This function is called spherical harmonics. Okay, this function is called spherical harmonics. Okay, keep this in mind. Now, see, when you change the Cartesian coordinate into spherical polar coordinate, similarly you have to change the operators. See, here the operator del square is in Cartesian coordinate. Now I am going to write del square in spherical polar coordinate. So what is the equivalent term for the del square in spherical polar coordinate is that 1 by r square dou by dou r. This is the expansion of del square operator, 1 by r square dou by dou r into r square dou by dou r plus 1 by r square sin theta into dou by dou theta into sin theta dou by dou theta plus 1 by r square sin square theta into dou square by dou phi square. This is the del square operator in spherical polar coordinate, but in our case r is constant, therefore this term, okay, become 0, right? That term doesn't appear because we have dou by dou r term. Dou by dou r becomes 0. So del square now it is equal to, right, we have 1 by r square here and here, so I will take 1 by r square as common, 1 by r square into 1 by sin theta into dou by dou theta into sin theta dou by dou theta plus 1 by sin square theta into dou square by dou phi square. So this is the del square operator. Okay, now I'll put this in the equation. Let me take this as equation number 1. I'll put this value in equation number 1. So So equation number 1 becomes, so in equation number 1 we have minus h bar square by 2m. Then in the place of del square I'll put this. Okay, we have 1 by r square here, so I'll write 1 by r square here. Okay, yeah, this is r square, so, and the operator 1 by sine theta into dou by dou theta into sine theta dou by dou theta plus 1 by sine square theta into dou square by dou phi square. Okay, and the wave function now it is represented as y, which depends on theta and phi variable, equal to e into y theta phi variable. Y depends on theta and variable. So this is the equation. Now you know very well m into r square is nothing but moment of inertia. Okay, so I can also write this as minus h bar square by 2i. Let me keep this thing as such, y theta phi equal to e into y theta phi. You need not write this theta phi again and again. Okay, now see, I have converted this m into r square into a moment of inertia. Okay, now I'll bring this term to the right hand side, or you multiply both sides by 2i by h bar square, minus 2i by h bar square. So you will get, let me do it in the next page. Yeah, see what I'm going to do, I'll bring this term to the right hand side. So in the left hand side we have, and in the left hand side I'll do one more thing, I'll bring this, okay, let me write once, 1 by sine theta into dou by dou theta into sine theta dou by dou theta. I'll bring this function y inside, so that y will come here. Okay, yeah, then plus 1 by sine square theta dou square by dou phi square. I'll bring this y here. Okay, so I have brought this y and I'll keep with the operator. Okay, so operator will operate on the function y now, equal to, in the right hand side we'll get minus 2i e by h bar square into y. Okay, yeah, so we have obtained an equation like this. Now what I'm going to do is that, let me solving this equation is somewhat difficult because this function y depends on two variables, theta and phi. So I'm going to solve this by using the method of separation of variable. Okay, so by applying method of separation of variables, okay, according to which this y, which depends on theta and phi, this can be separated into two. One depends on theta alone, the other one depends on phi alone. Listen, the theta function, it is the usual way of writing theta function. Okay, theta, big theta, which depends on theta variable, and the other one is big phi, which depends on phi variable. This is a usual notation. Y is divided into two functions. One depends on theta alone, the other one depends on phi alone. Okay, so you can also write this simply as theta into phi. Every time you need not write theta, phi like that. Okay, you can put just theta and phi. So now in the above equation, wherever y is there, I'll put this one. So if I put here, if I put in the place of y, if I put theta and phi, see this operator dou by dou theta will operate only on theta function. Therefore phi part is constant, you can keep it out. So phi into sine theta into dou by dou theta. Okay, then sine theta dou by now this theta will remain there, theta by dou theta. Remember, big theta is a function, small theta is the variable. Okay, plus similarly if I put theta and phi here, this operator dou square by dou phi square, this operator operates only on the function phi. Okay, therefore theta you can keep as constant, so you can take it out. So theta in by sine square theta into dou square big phi by dou phi square equal to minus 2ie by h bar square into theta into phi. Let me write like this. Now what I'm going to do is that I'll take this term, that is my 2ie by h bar square. I'm going to take this term, I'll put, because 2ie h bar square is a constant for a given particle, okay, and for a given energy, right? For a given energy and for a given particle, this quantity is a constant. 2ie by h bar square is a constant. Let me take that constant as lambda. Okay, so this equation can be written as big phi by sine theta into dou by dou theta into sine theta dou by you can write directly exact differential d, right? Full differential, right? Instead of partial differentiation, you can write full differentiation, because now the function depends only on theta. Similarly here, big theta by sine square theta into d square phi, because why am I changing partial differentiation into full differentiation? Because the function depends only on one variable now. Okay, yeah, equal to minus lambda into theta into phi. Okay, right. Now I'll bring this term to the okay, before that let me do one more thing. So I'm going to multiply throughout the equation by sine square theta and divide throughout the equation by big theta and big phi. Okay, so what will happen here? Phi cancel, sine theta, sine square theta, if you cancel, you get 1 sine theta. So sine theta into d by d theta into sine theta d big theta by d theta. Okay, plus here theta cancel, sine square theta cancel, so you're left with only 1 by phi into d square phi by d phi square equal to minus lambda into sine square theta. Okay, if you multiply here, sine square theta will come, theta phi cancel. Okay, now what I'm going to do, I'm going to bring this term to the right hand side and this term to the left hand side. Okay, so if I do that, what we'll get is, yeah, let me write the next page. So we have sine theta d by d theta into sine theta d big theta by d theta plus not plus, I'll bring this term to the right hand side, so it will become plus lambdas into sine square theta plus lambda into sine square theta, and I'll bring this term to the right hand side, so you'll get minus. So you'll get minus 1 by phi into d square phi by d phi square. Okay, yeah, see this equation. In this equation, the left hand side consists of only theta part. Okay, it depends only on theta. Left hand side depends only on theta, whereas right hand side depends only on phi. Listen, left hand side depends on one coordinate theta, right hand side depends on only on the coordinate phi. Theta and phi are different, but since they are equal, it means this should give you a constant and this should give a constant, and those two constants are supposed to be same. Okay, only then these two quantities will be equal, because theta and phi are not equal. So this should give a constant, this should give a constant, and those two constants should be equal. Let me take that constant as let me take the left hand side and right hand side equal to ml square. I'll equate left hand side and right hand side to the same constant ml square. So if I equate this to ml square minus 1 by phi into d square phi by d phi square equal to ml square. I'll get an equation. But the equation, shall I give a number to this equation? One second. Yeah. Before that, I'll give this as equation number 2. This as equation number 3. Okay. And I'm going to give this as equation number 4. Okay. Now bring this phi to the right hand side. So you can rearrange this equation and you can write like this directly. I'll bring this phi here and minus, multiply both sides by minus. So this become plus and this become minus. So I'll get minus ml square phi. Bring the minus ml square phi to the right hand side. So plus ml square into phi equal to 0. This equation we have already familiar with. We have already seen this equation. It is just particle on a ring system. It is exactly similar to particle on a ring, which we have already worked out. What is the wave function for this? Yes, the wave function phi, which depends on the variable phi, equal to, we have already solved this problem, so I am going to write the solution directly, which is 1 by square root of 2 pi into e power I ml into phi. This is the wave function, right, for phi part. This is the expression for the phi part, and you also know that ml can take value 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. These are all the possible values of ml. So ml is a quantum number. It can take only certain allowed values. Okay. So this phi part we know already. Now, so here I have equated the right hand side. Now, if I equate the left hand side, I'll get another equation. Let me write here sin theta into d by d theta into sin theta d big theta by d theta plus lambda into sin square theta. I'll take this value equal to ml square. Okay, and I'll take this as equation number 5. Right? I'm sorry. I'll give equation number 5 to this and equation number 6 to this. 6. Okay. Yeah. Now, to solve this, what I'm going to do, I'm going to divide throughout by sin square theta. Okay. So multiply throughout by 1 by sin square theta. So what will I get is 1 by sin theta, sin square theta, if you cancel it, you will get 1 by sin theta into d by d theta into sin theta d big theta by d theta plus here sin square theta, sin square cancel, you get lambda, and here we will get ml square into sin square theta. Okay, I think I may have committed any mistake. I made a mistake. See here what I did here, when I multiply by sin square theta by big theta phi, okay, here phi cancel, the theta will remain, right? So the theta I left it. I'm sorry. So keep this change in my paper. Yeah. So I just left this big theta. Big theta should be there, right? So what will I do is I'll simultaneously multiply throughout the equation by big theta by sin square theta. I'm multiplying by big theta by sin square. So here theta cancel, you'll get 1 by sin theta. Okay, here lambda into sin theta will come, sin square theta cancel, so you'll get lambda into big theta. Here I'll get ml square theta by sin square theta. I'll bring it to the left hand side, so I can write directly this as lambda minus ml square by sin square theta. Okay, I'll take this big theta out, theta equal to 0. Right? I think you can easily follow this equation. Right? Yeah, I just missed this theta, so I'll resubstitute that, and this is the expression. Now we need to solve this equation. Okay, to solve this equation, what I'm going to do is that let me take cos theta as x. Okay, let me put cos theta equal to x. So I am changing the variable from theta to x. If you change the variable, you should change the limit also, right? What is the limit for theta? The limit for theta is theta will vary from 0 to pi. Okay, it is a azimuthal angle. Azimuthal angle will vary from 0 to pi. Now I am changing the angle theta to a new variable x. Therefore, if I put theta equal to 0 here, cos 0 is 1. If I put theta equal to pi here, cos pi is minus 1. Therefore, the x limit will become 1 to minus 1. Okay, plus 1 to minus 1 is the x limit. Okay, so I'm changing, I'm just taking this cos theta as x, right? Then if I differentiate this, I'll get minus sin theta into d theta equal to dx. Okay, yeah. Similarly, I'll take this part, that is a differential of big theta. Let me take this as equation number 7. Okay, differential of big theta by d theta can be written as, yeah, by using this differential equation, we can write this as, you can also write like this, d theta by dx into dx by d theta. You can write like this. Okay, what is dx by theta? I'll bring d theta here. So dx by d theta equal to minus sin theta. So this can be written as minus sin theta into differential of big theta by dx. You can write like this. Okay, and if I remove this big theta, you can write d by d theta is nothing but equal to minus of sin theta into d by dx. Okay, so now let me substitute all these things here. So equation 7 will become like this. Okay, here we have 1 by sin theta. I'll keep it as such. In the place of d by d theta, what is d by d theta? D by theta is this, minus sin theta into d by dx, bracket. Here we have sin theta. I'll keep it as such. What is d big theta by d theta? That is equal to minus sin theta. So minus of minus here, I'll put minus here, minus sin theta into sin theta becomes sin square theta into d big theta by dx. Okay, plus lambda minus, I'll keep this ml square as such, by sin square theta is nothing but 1 minus cos square theta. Since cos theta is x, we can directly write this as 1 minus x square. Okay, 1 minus x square into theta equal to 0. Okay, now we got an equation like this. Let me simplify this. Sin theta cancel here. Minus, I'll bring it out. Minus or minus become plus. So I'll get a simplified expression d by dx of sin square theta. What is sin square theta? 1 minus cos square theta. 1 minus cos square theta is nothing but 1 minus x square. Okay, so we'll have 1 minus x square into d big theta by dx plus lambda into minus ml square by 1 minus x square into big theta equal to 0. So we got an equation like this, and this equation, let me take this as equation number 8, and this equation is a very famous equation called associated Legendre equation. But in associated Legendre equation, we won't use the symbol theta. We use theta is now variable of x. Okay, we use the symbol p. So I'll replace this theta into actually PL of mx. Okay, actually if we solve this, we'll get theta. That theta is called Legendre, associated Legendre polynomial. I'm sorry, associated Legendre function. So this equation, what I'm going to do, first I will replace this theta by PL of m. So PL of m, every time you need not write PL of m. So let me put simply P of x. Okay, so d by dx 1 minus x square PL of m of x by dx plus lambda minus ml square by 1 minus x square into PL of mx equal to 0. I have brought it into a standard notation, and this is what we call as associated Legendre differential equation. Okay, this equation is called, let me write here, this equation is called associated Legendre differential equation. Okay, if you solve this equation, you will get the associated Legendre function PL of mx. This is a usual way of writing the Legendre function. In the Legendre function, m represent order and L represent degree. Okay, so this is Legendre function of order m and degree L. Okay, yeah. So I will take this as equation number 9. This is called associated Legendre differential equation, and this is also associated Legendre equation, but only thing is here we have theta. Okay, now I have changed the theta into PL of m. Therefore, these two are actually Legendre differential equations. So I stop here. In my next lecture, I'll show you how to solve this Legendre differential equation. Okay, but before that, before completing today, let me give one information here. What is that? Listen, what happened if x square become plus 1 or minus 1? You know very well, the range of x is, okay, x range is 1 to minus 1, right? So if x is plus 1 or x is minus 1, if I square it, I'll get x square as 1. If I put x square equal to 1 here, 1 minus 1 becomes 0, something by 0 become infinity. Okay, the function, so the Legendre differential equation will diverge. Okay, if x approaches or x square approaches plus 1, okay, the equation diverges, right? Therefore, we have to concentrate on that. We should not allow the equation to go to infinity. Okay, so we have to make something on the product of this ml square and theta. Okay, let me discuss that in the next class. Okay, in the next lecture. I stop here. Okay, thank you.